This is slide number 46 and I am your presenter Asloob Mudassar. Fraunhofer diffraction formula. To derive the Fraunhofer diffraction formula, we start with the Fresnel diffraction formula given in equation number 33 and is reproduced below in equation number 66. So you can see that this is the expanded form of the Fresnel diffraction formula. Now using this formula we shall derive the formula for the Fraunhofer diffraction. The Fraunhofer diffraction approximation that we are going to use is given in equation number 67, which is stated as k over 2z multiplied by zeta square, the maximum value of zeta square plus eta square, that should be much less than 1. You know that this quantity has all the variables positive. So zeta is positive due to its square. Eta square is also a positive quantity greater than 0. So all the parameters are greater than 0. So k over 2z multiplied by zeta square plus eta square, the maximum value of that one. So this quantity, this product, this whole term is greater than 0 but less than 1 in equation number 67. Under this approximation, the quadratic phase factor at the input plane vanishes. So you see that you can see that there are two quadratic phase factor. One is with the input field, which is e to the power iota k over 2z eta square plus zeta square, and on the outside the integral we have another quadratic phase factor associated with the output plane. This is e to the power iota k over 2z multiplied by x square plus y square. So you see that only the phase factor which is within the integral, within the curly bracket, will be affected by this approximation given in equation number 67. So using that approximation, we have shown in equation number 68 that e to the power iota k over 2z multiplied by zeta square plus eta square, the maximum value of that quantity is equal to e to the power iota, and you know that this quantity which is given in equation number 67 is approximately equal to 0, because being much less than 1 and of course greater than 0. So this quantity is approximately equal to 0. So we can say that this quadratic phase factor associated with the input aperture is equal to 1, as given in equation number 68. So using that one in the formula given in equation number 66, we come up with another formula given below. So in equation number 69 we have u of xy is equal to e to the power iota kz or iota lambda z multiplied by the quadratic phase factor at the output plane, which is e to the power iota k over 2z multiplied by x square plus y square, and within the integral, which is minus infinity to plus infinity, we have the field u of zeta and eta, and of course this is another term e to the power minus iota 2 pi fx into zeta plus fy into eta. You see that you can recognize this integral as the Fourier transform of the field, which is u of zeta and eta. So you see that replacing the integral, we have represented it in the symbolic form, that it is the Fourier transform of u of zeta and eta by using the tau type operator. So you see that this form, which is given in equation number 69, is referred to as the Fraunhofer diffraction formula. So you see that what we have done is that we have derived equation number 69 from equation number 66, which is the Fresnel diffraction formula, under the condition given by equation number 67. Remember that zeta square plus eta square is actually the distance from the origin to the point, actually the square of the distance from origin to the point, and the point is zeta and eta. So if you apply the distance formula from the origin, which has the coordinate 0 0, and the other point on that plane is zeta and eta, the distance formula between these 2 points, the square of that distance will be equal to zeta square plus eta square. So you see that this quantity is much less than 1. It means that we actually limit the dimensions of the aperture in such a way that it is multiplied by k over 2z, and then that is also much less than 1, although k is a very large number. So this is the formula diffraction, Fraunhofer diffraction formula. Due to the absence of e to the power iota k over 2z into zeta square plus eta square, the symmetry of the Fraunhofer diffraction formula is lost. So if you look at equation number 66, which is the Fresnel diffraction formula, it is very much symmetric. You have two quadratic phase factor. One is at the associated with the input plane, the other one is associated at the output plane. which is lying outside the integral. But you know that here we have only one quadratic phase factor formula, only one quadratic phase factor which is associated with the output plane. So we can say that due to the absence of e to the power iota k over 2z multiplied by zeta square plus eta square, the symmetry of the Fraunhofer diffraction formula is lost. Now we cannot write this in the convolution form. So convolution form of the Fraunhofer diffraction formula is not possible. If we cannot write anything in the convolution form, it means that the space invariance is destroyed, and the point spread function of the PS and the point spread function, which we call as PSF, cannot be worked out for the Fraunhofer diffraction formula. So how we can then write, because we need to write the point spread function. So what we do is that we adopt the point spread function which was written for the Fresnel case, and we adopt that formula also for the Fraunhofer case under the condition that listed above, that is under this condition given in equation number 67. So using that condition, we can use the formula, the Fresnel point spread function given in equation number 70. So kappa of xy is equal to e to the power iota kz over iota lambda z multiplied by e to the power iota k over 2z. Within the bracket we have x square plus y square. So this was actually the transfer function that we wrote down for the case of Fresnel. We are also going to adopt this for the case of the Fraunhofer diffraction formula. But you know that we need to remember the condition on the value of z, which is obtained from the equation number 67 and rewritten in the form of equation number 70 in the inequality given in equation in label 71. So you can see that here we have written that z is much greater than k over 2 multiplied by the maximum value of the zeta square plus eta square. So you see that equation number 7, which is basically related with the Fresnel diffraction formula, can be adopted as the point spread function for the Fraunhofer field, provided we follow the z condition on the z given by equation number 71. The Fraunhofer diffraction formula can be observed for very large distances, much greater than the dimensions of a laboratory when the size of the input aperture is couple of centimeters apart. So you see that we need to have a long laboratory if we want to observe this one. Fraunhofer field is can be observed at the Fourier plane. So this is the method that we can also observe that one within the laboratory space, but we have to do some modifications. To observe it within the laboratory scale, two approaches can be used. The number one approach is that illuminate the object with the plane wave and use a well-corrected biconvex lens after it at a distance equal to its focal length and observe the field at the back focal plane of the lens. That is, put the aperture in the front at the front focal plane of the lens and observe the Fourier transform at the back focal plane of the lens, provided the illumination to that input object was due to the unit amplitude normally incident plane wave. The second approach is that illuminate the aperture plane with a spherically diverging beam, which in the absence of the aperture would focus at the plane called the Fourier transform plane. So illuminate the object with the spherically converging beam, and if you remove the object, the beam will focus originally at some point, and you know that plane which contains the which would contain the spherically converging beam would be the Fourier transform plane where we can observe the Fraunhofer diffraction field. Now, applications of the Fraunhofer diffraction formula. There are 4 applications that will be discussed in this course. One is the Fraunhofer diffraction by a rectangular aperture. The second is Fraunhofer diffraction by a circular aperture. The third one is Fraunhofer diffraction by a thin sinusoidal amplitude grating. The fourth one is the Fraunhofer diffraction by a thin sinusoidal phase grating. So amplitude grating and phase grating both will also be discussed. Now here in the slide number 46, we are only going to present the first case, that is the Fraunhofer diffraction by a rectangular aperture. So consider a rectangular aperture of sides 2wx and 2wy centered at the origin of the zeta eta plane and is normally incident by a unit amplitude normally incident plane wave. The amplitude transmittance of the aperture, since our aperture is rectangular, the amplitude transmittance is given by equation number 72. So TA, which is the amplitude transmittance at the coordinate zeta and eta, is equal to rect of zeta over 2wx multiplied by rect of eta over 2wy. So you see that in the zeta direction we have the width of the aperture which is equal to 2wx, and along the eta direction we have the width of the aperture which is 2wy. So ignoring, so you see that since we are illuminating this object which is represented by the amplitude transmittance given in equation number 72 by a unit amplitude normally incident plane wave. So our amplitude is equal to 1, and you know that the phase value on that plane will be constant, which we can drop. So ignoring the constant phase term, the field just before the rectangular aperture is equal to 1 due to the amplitude of the plane wave, and the field just after the aperture is given will be given by equation number 73, because the equation number 72 multiplied by 1 is the same as equation number 73. So now we have changed the labels on the left hand side. So rather than writing the amplitude transmittance as in equation number 72, we are representing it as a field just after the rectangular aperture, which is u of zeta comma eta is equal to rect of zeta over 2wx multiplied by rect of eta over 2wy. So using equation number 69, the Fraunhofer field is given by. So you see that we have represented equation number 69, which is the formula for the diffraction, for the Fraunhofer diffraction was given over here. So you see that we have to evaluate the Fourier transform of the field u, which is the input field, and then we have to plug in that plug back that value of the Fourier transform given of the Fourier transform in equation number 69. But we need to, you know that when we take the Fourier transform of u having the coordinates zeta and eta, the Fourier transform will appear as fx comma fy, which are the Fourier parameters. So on the right hand side we shall have the Fourier parameters, but on the left hand side we have space variables which are x comma y. So you see that we have to replace the Fourier frequencies fx comma fy by some relationship, so that we can go back to the space variables. And so we have to evaluate that integral at those we have to evaluate the Fourier integral at the values which is given in equation number 74, that is fx is equal to x over lambda z and fy is equal to y over lambda z. So take the Fourier transform as given in equation number 74 and then evaluate that one at fx and fy values. So let's take the Fourier transform of equation of the input field that is the Fourier transform of u of zeta and eta is equal to, you see that we have written here the integral, Fourier transform integral containing the field which is u of zeta and eta, and now we are plugging in the value of the u of zeta and eta in terms of the two rect functions, and at the same time we are separating this double integral into two single separable integrals, one integral on the zeta coordinate, the other integral on the eta coordinate as given in the second row of equation number 75. So you see that now we can remove the two rect functions. In the first integral, the rect function is removed, but the limits has been changed from wx to from minus wx to plus wx, because in these limits the rect function is 1 and outside these limits the rect function is 0. And similarly in the second integral we have replaced the infinite terms on the integral by minus wy to plus wy, and the rect has been set to 1. And you know that if you take the integral of these quantities, we have from the first integral we have 2 times wx multiplied by sink of 2wx into fx, and the second integral will give you 2 times of wy multiplied by the sink of 2wy into fy. So you see that we have evaluated the Fourier transform in terms of the two sink functions, but you know that we have 2wx multiplied by 2wy is actually the area of the rectangle. That area will be represented by capital A. So the last line of this Fourier transform is that that is the area of the rectangle multiplied by the sink of 2wx multiplied by fx and the sink of 2wy multiplied by fy. So 75. So equation number 75 gives you the Fourier transform of the input function. Next step is to evaluate this Fourier transform at the coordinates fx is equal to x over lambda z and fy is equal to y over lambda z. As listed, you know that on both sides we have listed these fx and fy values. So on the left hand side these are the symbolic representation that we are writing, but you know that actually we shall be using these fx values and fy values on the right hand side. So fx in the sink will be replaced by 2wx 2wx into x over lambda z, and similarly using 2wy and plugging in the value of y, we have the argument of the second sinc function as 2wy multiplied by y over lambda z. So this is equation number 76 after we have converted that one into the space coordinates which are x and y. Now we have to plug in this Fourier transform back into equation number back into the previous equation. So equation number 74. So we shall plug in the Fourier transform over here on the right hand side and plugging in the value and plugging that evaluated Fourier transform in equation number 74. So after plugging that one, we obtain equation number 77. Which is, you know, that u of x comma y, the field at the output coordinates x comma y is equal to e to the power iota k z over iota lambda z multiplied by the quadratic phase factor associated with the output plane which is e to the power iota k over 2z into x square plus y square, and the two sinc functions multiplied also with the area of the rectangle we are using. So a multiplied by sinc of 2wx into x over lambda z and sinc of 2wy into y over lambda z. So equation 77 is the field that we have calculated using the so this is the Fraunhofer field at the output plane. So the intensity, so this is the field, you know, that if we want to write down the intensity, what we have to do is that we have to use the relationship, we have to multiply u with its complex conjugate as given in equation number 74. So we have intensity in the second step, that I of xy is given by a square over lambda square z square multiplied by the sinc square of 2wx into x over lambda z and multiplied by sinc square of 2wy into y over lambda z. So this is the two-dimensional expression for the intensity of the Fraunhofer diffraction pattern due to a rectangular aperture at the point of observation which is x comma y. To plot this intensity, we set these parameters. 2wx, that is the width of the rectangle along the x direction, is equal to 6 mm, that is along the zeta axis, and 2wy is equal to 4 mm, which is the width of the rectangle along the eta direction. And lambda we are using is 632.8 into 10 to the power minus 6 mm, which is the red wavelength of the helium neon laser, and the distance that we are using is z, capital Z is equal to 1200 mm. So you see that all the parameters we have used, we have set up, and using these formulas in equation number 78, we are plotting the intensity. And assuming that because we have derived this formula, assuming that the rectangle was illuminated by a unit amplitude normally incident monochromatic plane wave. So you see that we have now two plots over here. The 3D plot and the two-dimensional plot, the 2D plot of the intensity are shown at the top and bottom respectively. So let's read about these plots. Width of the main lobe in the y direction, which is parallel to the zeta axis, is larger than its width along the x direction, which was parallel to the eta axis, which is parallel to the zeta axis. The aperture width in the eta direction is smaller than its width along the zeta direction. It is because due to this one, because we have set, you know, that the different along the, you know, that zeta direction we have width 6 mm, and along the eta direction we have the width which is 4 mm. And so if the aperture is smaller, the width in the Fraunhofer diffraction will be larger in that direction. And the two-dimensional plot is also shown over here because we wanted to appreciate the side lobes which are now prominent. So main lobe and the side lobes are also prominent over here in the second row, which is in black and white. So when the rectangular spacing is narrowed down in one direction, the main lobe in the Fraunhofer field will be broadened up in the same direction and vice versa. So main lobe and the nearby side lobes can be seen in both the figures. For further investigation, the Fraunhofer intensity expression for one-dimensional case obtained from equation number 78 is given below. So you see that the three-dimensional and the two-dimensional plots cannot be appreciated very much. So we need to have one-dimensional plot of that one. So we are using only a variable x. So I of x, and we are dropping the y-dependent quantities. So I of x is equal to a over lambda z and multiplied by the sine square of 2wx into x over lambda z. So this is equation 79. So we are going to plot this equation. Let's produce the plots of this intensity for different values of z. Z is in millimeters. So the z value will range from z is equal to 1200 millimeter to z is equal to 1800 millimeter. Other parameters are 2wx, width along the x direction, that is along the zeta direction is 6 millimeter, and we have lambda, the wavelength of helium neon laser operating at red wavelength. Now you see that we have we have shown all these plots from look at the plots that we have chosen from z is equal to 1200 to z is equal to 1800. So you can look at these plots. The one thing which is very prominent is that the main lobe is going to be broadened, and the second thing is that the side lobes are going to be smoothened. So let's read the statements. Main lobe expands further with the distance away from the diffracting aperture. Smoothness of the main lobe and the side lobes increases with z. So the smoothness will also increase and the main lobe will also expand. The peak intensity value of the main lobes decreases with z and is reduced by 37% over the propagation distance shown. So in the last graph, though we have shown the same intensities because we have plotted the normalized plots of these peak values which are the same over here, but you know that actually we have noticed that in the last plot, which was at z is equal to 1800 millimeter, there the intensity, there the peak value was reduced in comparison with the plot at z is equal to 1200 by a percentage or by a 37%. So but here you know that we have shown on the normalized plot. So these plots you can see that very clearly explain. So you see that these plots when plotted in 2 dimension or 3 dimension, we cannot appreciate their beauty, but here we can very well appreciate that how the main lobe will expand and how the side lobes are smoothened out. So these are the plots of the Fraunhofer intensity in one day at different z distances, and the z distances are in millimeter. Now the problem is that can we find the spacing of the main lobe, that is the width of the main lobe at its foot? Yes. The size of the main lobe, which is delta x, is equal to 2x naught at the foot where the curve intersects the x-axis, can be found using the equation given in equation number 80. So I of x naught is equal to a over lambda z sin square of 2wx into x naught, because we have replaced x naught over here, over lambda z is equal to a over lambda z, and you know that we are going to replace sinc function by the sine function, and you know that sinc of x is equal to sine of pi x over pi x. So pi will be multiplied up in the denominator and in the numerator and in the denominator. So having applied that one, the curly bracket has a square due to the sinc square, and we have set that one equal to 0. So now we have to solve this quantity. You know that the denominator is not matter, so we have to only solve the quantity which is the sine function, because the sine has to be 0 if this intensity has to be 0. So in equation number 81, we have set the argument of the sine function equal to sine inverse of 0, and the sine of inverse sine will be 0. Sine inverse of 0 occurs at integer values of pi. So we have set it equal to n pi. And now we are using n is equal to 1, so that we can find the first two zeros on the center of the peak. That is the 1 0 on the right hand side, the other 0 on the left hand side. And you know that solving this, we have delta x is equal to 2x naught is equal to 2 times of lambda z over 2wx. So this is 2x naught is actually width of the main lobe at the points where it intercepts the x-axis, and we have denoted that one by delta x. So delta x is equal to 2x naught is equal to 2 times of lambda z over 2wx. So equation 82 gives you the width of the main lobe. So this gives the full width of the main lobe in the Fraunhofer diffraction at its foot. So this is the end of slide number 46.